asking to find the limits algebraically.
Okay.
And so it says x, the cube root of x, or x to the power of 3, minus 125.
Okay.
Over there, x squared minus 9x plus 20.
Okay. What's the top? What's the top? Is that it? We're simplifying this? Is that it? Are we simplifying this?
That's it. And then it wants you to find the limit as x approaches 5.
Okay. Well, the top becomes 0. I'm betting the bottom becomes 0. 25 minus 45 is 20, plus 20 is 0. So how do we handle 0 over 0?
You have to pull something out of it.
Well, we got to factor. If we can factor and then cancel something, then reapply x equal 5, we'll find that it's not 0 over 0 anymore. So how do you factor the top? What is the top called?
The cube rule?
Difference of perfect cubes.
Okay. So it would be x minus 5. Times x squared plus 5x plus 5?
It's, yep, plus 25, not 5. In other words, it's x squared plus a times b plus b squared. In other words, if I list the formula for difference of perfect cubes, it's a minus b times a squared plus ab plus b squared. That's what you got to remember is that. Now factor the bottom. And what is almost certainly one of the factors of the bottom? X minus 5. I mean, we almost know that without even looking at it. What's the other factor?
X minus 4.
Okay. Now we can cancel that one with that one. And now when we resubstitute x going to 5, the bottom goes to 1. So we know we do not any longer have 0 over 0 problem. What do we have? What does the top go to?
Wait, what?
What number does the top go to?
Oh, 125.
Substitute x of 5.
Yeah, so you want
so 25 plus 25 plus 25 is 75.
Oh.
And the bottom goes to 1. So that's the limit.
Another one that I have trouble with.
Okay.
So, turn the next to find the limit as x approaches, right?
Well, the audio is not good on my end when we're doing it this way. I can hear you fine, I just can't understand what you're saying really well. What's the limit again?
As x approaches 0.
What's the function?
X plus 5 plus b squared minus 25.
Minus what? 25?
25.
Okay.
Yeah, over x. Over x.
Oh, over x? Okay.
Yeah.
I got it.
Sorry.
That's all right. Not your fault. All right. So again, we have 0 over 0, right?
Yeah.
Okay. Well, let's see if we can get rid of some stuff. Expand the top. plus 10x.
Plus 25 minus 25 of it. Just kidding, I think it's 15 on this.
Okay, the 25s go away. Now factor the top.
Yeah, so then you get x times x plus 10 over x.
X's cancel, reapply the limit. What do you get?
X minus 10.
No. When I say reapply the limit, I mean resubstitute 0 for whatever x you see left. So that goes to 10. You understand what I meant?
Yeah.
Okay, cool. Got another one?
Yeah, this is different.
Okay.
Notation. So the solution is 5, 9, 13, 17,
Okay.
21, and then dot, 129.
And then dot, what's 429?
129.
129?
Yeah.
And the question is, how many terms are in the series?
No, it was you don't hear about it.
You could not understand a word you just said.
It was
On your GoToMeeting, turn the mic and speakers on and say that again.
on my computer?
Yeah, let's see if we can use the audio of GoToMeeting.
Okay.
Because I can't make out what you're saying through my other audio. Okay, say it again.
All right. It wants us to find, or it wants us to write the thing in sigma notation.
Ah, okay. And boy, what a difference in the audio. I can hear it crystal clear now. All right. So, is this arithmetic series?
Yes, because it's adding 4 each time.
Right. Okay. So we're going to have something that looks like, God, I got to figure out how to put these in sigma notation. Let me think for a second. Let's see. If it's, except it's not, hold on a moment. I did this before once with you, and I forgot how I did it. Let's see, how are we going to get 5 as a first term? We're going to have n plus 4. We're going to have n times, let's see, this is 4 plus 1. This is 2 times 4 plus 1. This is 3 times 4 plus 1. So let's see. Everything, the n is the multiplier, and we have 4 plus 1. So it's, the plus 1 is outside. There it is. And I can figure out what this last one is going to be. But that does the trick, doesn't it?
Yeah.
Okay.
I think
So how do we figure out the last one? Where does n go to?
on the top.
Well, we need to divide 129 by 4.
Oh, jeez. Okay.
All right. So if I divide 129 by 4, I get 32. So the last term should be an n of 32. Does that give me 129? 32 times 4 is 128 plus 1, yes. So that's how you do it. Actually, it was kind of enlightening figuring out how to do that. Notice what I did up top. I rewrote the series in a way that I could understand it better in sigma notation. In other words, that was 4 plus 1, that was 2 times 4 plus 1, that was 3 times 4 plus 1, that's 4 times 4 plus 1. That allows me to figure out exactly how the sigma notation must look. Because I can see what's counting up here is that's 1 times 4 plus 1, that's 2 times 4 plus 1, that's 3. In other words, what's going 1, 2, 3? Well, that's what n does. So that tells me that it has to be n times 4 plus 1.
Okay.
Well, give me another one of those. That was fun now that I know how to do them.
I don't know if I have any more. That's the one I have on my review.
I was kidding anyway. I'm sure that you'd give me one that was not that easy to do, and I probably wouldn't be able to figure it out. So, converting to sigma is kind of tough. But
Yeah.
that's kind of the secret, I think, is the way I did that one. That really was helpful. I didn't even know that that's what you were supposed to do. But I had figured it out from the last time you had that problem. I remembered. All right, what else? We got 13 minutes.
Okay. This one wants you to solve the log equation of log base 4x, 4, and then at big X, yeah, plus log base 4, and then parentheses x minus 3 equals 1.
Okay. What are we going to do with these two logs? If I can turn this into a single log function, then I can apply the conversion to get it into exponential format and then solve it. How do I take these two logs and turn them into one log?
You can multiply them, right?
Well, the sum of two logs is the same as the log of the product of the two arguments. So this thing is the same thing as x times x minus 3. Okay, that's step 1. Now we only have one log. So now I can say, what? Convert that to exponential format.
So x times x.
Here's the way I do. You probably, everybody has their own way of memorizing this. But when I'm going from log to exponential, it's the number on the far left raised to the power of the number on the far right equals the argument. So when I'm solving this, it's 4 to the 1 equals x squared minus 3x. Or 4 equals x squared minus 3x. And now that's relatively easy to solve. That's a quadratic. So I've got x squared minus 3x minus 4 equals 0. Factoring, that's x minus 4 times x plus 1 equals 0. Gives me two solutions, and almost always one of these solutions is going to be extraneous, meaning impossible. Well, which one is not possible? We got a solution of 4, x equal 4, or x equal minus 1. Can x be equal to minus 1?
No.
No, you cannot take the log of a negative number. You can't even take the log of 0. So if one of these solutions violates the domain, then you throw it out and you only have one solution, x equal 4.
Okay.
And furthermore, let me suggest that when you're checking the domain, always go back to the first function, not the second one. In other words, when I said that this second line is the same as the first? Not totally true. In other words, yes, I can apply the rules of logs to get to this point, but they're not the true in the same manner in that you can't check domain down here. You have to check the original domain, always. Because sometimes one of those numbers might pass this domain, and it would still flunk the original one. In other words, let me give you an example. If I had log x plus log x, like that, well, that's going to give me the log of x squared, right?
Yeah.
Now, if I were to get a negative solution, it doesn't flunk it down here. That negative number turns positive when I square it. But I still cannot have a negative x because it violates that domain up there.
Okay.
So always check in the original, and they'll give you problems where it will not flunk the domain test at that step, but it will flunk it if you go back to the original.
Wait, okay, so should you use a calculator for that? And just plug it in and see if it works?
No, you don't need to use a calculator. What was it?
Check for the negative.
What was the original? Log base 4 of x plus what?
-3.
Okay. One of our solutions was 4.
Yeah.
Well, the log base 4 of 4 is 1. And the log of 1 is always 0. So that works. In other words, it happens to give us 2 log functions that we can do without a calculator. The log base b of b is always 1, and the log of 1 base anything is always 0. So 1 plus 0 is 1.
Okay. Interesting. Okay. Alright. Okay. No, this was the right one. I'm just gonna answer for you now. Alright. Alright. This one wants to determine the range and function.
Okay.
For, do we have time? Yeah. For -3 log base 2. Parentheses x minus 6 plus 4. In parentheses. Yeah. Okay.
What's the range of that?
Okay, so your range would be -infinity to infinity, always.
Well, hold on. Or did we start with this? I'm having little sound problems again.
Oh, yeah.
Okay. Do they want the domain or just the range?
Both.
What's the domain?
Would it be 6? Right?
Greater than or equal or what?
Greater than? Right?
Got to be greater than, not greater than or equal, because you cannot take the log of 0. So it's got to be greater than 6. However, the range on log functions, just if I were to take the range of this, that's -infinity to +infinity, all reals. In other words, you can only take the log of positive numbers, but you can get any number you want. In other words, let's look at a graph of the log function. It goes from -infinity up to +infinity. But you always have to have a positive x. In other words, it's asymptotic to the y-axis. So therefore, the range of this function is going to still be all reals. There's nothing that, in other words, we're going to take our log chart and we may shrink it, we may stretch it, we may move it right, we may move it left, we may move it up and down, but it doesn't change the negative infinity to positive infinity on the y, no matter what we do to it.
Okay. Alright. And then for the logs, the equation is always negative infinity to infinity for the range, right?
Well, I think it is. It certainly is for that, regardless of the base. And doing any reflections or transformations don't change anything. In other words, if I'm starting with this, no matter what I do to that curve, I'm not going to change the negative infinity to positive infinity, am I? Yeah. If I move it, if I reflect it over the x-axis, doesn't matter. It looks a little different. It looks like that, but it's still going from negative infinity to positive infinity. If I move it left or right, it doesn't matter. If I move it up and down, it doesn't matter. So, yeah, you don't need to work with anything just other than knowing that the range is always negative infinity to positive infinity. I think. I can't think of a case where it would change it.
Yeah.
Maybe if it were division going on or something like that, I don't know. But as long as it's just a log function that's being transformed or translated, not going to change the range. It might change the domain. The domain certainly could change because this domain is pretty specific. In other words, if I move that left, changes the domain. Or if I move it right. But there's no way to change the range by a transformation.
Yeah. Okay. Because even if you move it left and right, it's still...
Yeah, the range is still going to be negative infinity to positive infinity. Even if I change the shape, even if I reflect it over either axis. In other words, if I reflect it over the y-axis, it's still negative infinity to positive infinity.
Okay.
Maybe you got time for one more.
Alright. So, this one says, suppose the point 3, 1 satisfies the function f of x. What point would satisfy g of x when equal to negative 2 f of x over 2? Oh wait, no, just like in parentheses, x over 2. F of x over 2. That's weird. Plus 1.
I have trouble with these. I'm not sure I'm going to be able to do this in 2 minutes. Let's see.
Here's my question. Because the answer to it, I have the answer key. The answer to it is 6, negative 1. And I was just wondering, like, basically how you go about doing that.
Well, let's look at what each thing is doing. This negative 2 is a reflection over the x-axis and a vertical stretch by a factor of 2. This 1/2 x is a vertical stretch by a factor of 2. A horizontal stretch by a factor of 2. This is a vertical shift up by 1. So, if I had, let me see if I can figure out how to do these. If I had a curve that the point 3, 1 was on, let's pretend that that's the curve. We don't know what the function is. But what I know is that the function is being reflected. Notice that doesn't change its x value. right?
Yeah.
If I reflect that function, x value stays the same. But the 2 vertically stretches it. So it turns the 3 into a 6. The plus 1 doesn't change the x value of the function either. The 1/2 in front of the x is a horizontal expansion. So it would take this parabola and make it look like that. Well, that changes the y value.
Okay.
And the plus 1 changes the y value.
So it just brings it up. Could you just graph it to figure it out?
No, you can't, because they don't give you f of x. In other words, this is one that really requires you to apply the transformations to figure out where the new point's going to be. Okay? And we can kind of get it from this example. In other words, if I assume it's a parabola, well, the reflection doesn't change the x value. It does change the y value, though. So the y value would go from 1 to -1. If I was just doing minus f of x, it would make whatever my y value was on that point be negative. So if it was at 1, it's now at -1. With me?
Yeah. Okay.
And then I've got to move it up 1 because of this one. But the multiplication of 2 puts it back at -1. I can't really explain it in detail because I don't have time here, but that's the way to look at it. Make up a function for f of x, apply all of the translations and shifts and reflections, and figure out where your point ends up. And you'll find out that that point ends up at 6, -1. Okay?
Awesome. Thank you so much.
Good luck on your final. And if I don't talk to you again for a while, I'll probably talk to you in the fall.
All right. Thank you.
All right, Sarah. Have a good one.
You too. Bye.
Bye-bye.